Okay, so today we're going to learn about mass spring systems, and you might be bummed when you came across a section in the textbook because, if you took physics in high school, you probably left the final exam thinking, woohoo, no more physics ever again in my life. And then Math 240 showed up and said, psych. So you're probably pretty upset to see this, but it's brief. And also, if you compare it to section 8.6, which we don't do in this course, I think you'd be pretty happy to do spring mass instead of RLC circuits from electromagnetism. So we'll be talking just a bit today about the spring mass systems, where they come from, and what the cases you need to know for the exams and stuff. So I have written here the equation that we care about for the spring mass system. So there's a more in-depth process as to how they got all of this in the textbook, but pretty much you start with, and I'll draw a picture here. I didn't leave myself a lot of room. You have a mass, it's hanging on the spring, and it's attached to a ceiling or something. You initially hold it at rest somewhere, and you let it go, and it starts, bouncing up and down like that. And you're interested in recording the motion for whatever reason. So I just want to cover a bit about where these terms in the equation came from. So this first term here is this is from the motion of M. So this just is saying how M is moving in the space around it. This term here is due to the force of something like air resistance. So we have the mass moving, and as it's moving, it has to go through some medium. And so this medium is preventing it from moving. So if M is moving up, for instance, I have the air resistance trying to push it back down. So this is something like air resistance. We refer to it in this course as damping. Okay, that's a pretty important word. And then this last term here is due to the force of the spring. Nothing too fancy there. And then finally on the right-hand side, we have some outside applied force. So somebody is, standing there pushing the mass as it moves, and it's not part of your actual system, but you have to account for it anyway. So that's what we have here on this right-hand side. It looks like this. I selected colored pencil again. I don't know why I keep doing that, but whatever. Outside force, like this, pushing on your mass. Okay. But what we'll care about in this video is the special case where no one's touching your mass spring system, where you have a homogeneous differential equation to solve here. And that's what we'll cover in this video. So I just want to cover the possible cases you can get, and then pretty much do a practice problem so you know what you have to do with these systems. Okay, so we have a particular case that's the ideal case. So we consider where there's no air resistance whatsoever. So we say when C is equal to 0, okay? So there's no damping involved here. And if you look at our differential equation, that corresponds to just leaving out that middle term here. And you have this system. And again, we're only considering the case when we equal 0 in this video. And then what you would do is you would factor this down as you normally would. So this becomes d squared plus k over m applied to y is equal to 0. You would go through, I'm not going to in this video, and you'd find the roots of this polynomial, and you'd find your solutions that way. But the general form of an equation satisfying no damping is this. C1, you have cosines root k over m times t plus C2 sine of square root k over m times t. And what someone has done is they've played around with the solution. And so the one you'll be writing most of the time on your exam is this one here. So you have some amplitude A naught. You have cosine of omega naught t minus phi. So this omega naught here is defined just by the square root of k over m. This is your the frequency that your system naturally wants to vibrate at. So if I let it go and I don't do anything with it, it will move like this, right? And it will move at some sort of natural frequency. That's defined by square root of k over m. And then if you want to know where this a naught and this phi came from, you can look in the textbook. A naught is the maximum amplitude it reaches. And then phi is, if you're starting at t equals 0, it's this sort of phase shift. So you don't start exactly perfectly in line with your oscillations. You start a little below or above. That's just what phi means. So this is the case where you have no damping. Your solution you'll be using is this one here for this differential equation. Okay. And now let's consider the case where we do have damping. So when C is not equal to 0, and in fact we've defined C to be 0 or positive. So I'm just going to say when it's greater than 0. So we have damping here. Let's look at our differential equation and let's derive out some results here. So we have d squared y dt squared plus c over m dy dt plus k, that's not a k, k over m y is equal to 0. And so what we can do is we just leave all these constants in here for now because we're doing a general case. And we go ahead and factor this as we normally would any other second order differential equation. So this becomes d squared applied to y plus c over m d applied to y plus k over m times y is 0. So I can factor this out. D squared plus c over m d plus k over m applied to y is equal to 0. And then I can factor down this polynomial differential operator. And then I'm going to do so with the quadratic formula. So, you can't really factor this by looking at it. If you could, you'd be a genius, and you should be teaching this course. But what we can do then is we know the roots of this polynomial, R1 and R2, are going to be equal to this negative b plus or minus the square root of b squared minus 4ac, so 4k over m, and then the whole thing divided by 2. And then what we can do is we can play around with a little bit of stuff to make it better for us. So we can write this as negative c over 2m plus or minus, you do some factoring on the inside here to pull out this m, and you're left with c squared minus 4km inside the radical. And then what you do, we have these roots to our polynomial differential operator, right, R1 and R2, so those just become what we put in for our solution, right? So we have y of t then is equal to c1e to the r1t, plus c2e to the r2t. So this is just where our solution goes. But as you can see here, we have this radical. And we saw in a couple videos ago that when you have two roots possible here, you can have three different scenarios. You can have repeated roots where we should do that last. You can have two distinct real roots. So there could be a case where, R1 is equal to 1 and R2 is equal to negative 4. That's totally fine. We can have that case. We can have repeated roots where R1 is equal to 1 and R2 is also equal to 1. And then we had to do something different with our y of t. And then finally, we can have complex roots here. So you'll notice that if we were to have repeated roots, this thing here, this radical, would have to be equal to 0. that would go get rid of this entire term here. And we just have R1 and R2 be equal to the same thing, this negative C over 2M. And so if we have repeated roots, what we do then, and I can't write on this picture without it messing up, we use the second, maybe I can, no I can't. We use the second solution here, y of t is equal to negative C over 2M. And we check that condition just by making sure that this radical goes to 0. Okay, so that's repeated roots. If we have complex conjugate roots, this radical here has to be negative. We need something negative inside of there. So that corresponds to c squared minus 4km being less than 0. And then I can rearrange stuff and say, not c2, c squared. I can rearrange stuff and say that c squared over 4km has to be less than 1. If I do that, then I have the repeated roots here in my radical. So R1 and R2 are complex. We know that when that happened, out popped some sines and cosines, right, from last video. And so we use this first solution, 8.5.11, to describe the scenario when c squared over 4km is less than 1, and that corresponds to underdamping. And then finally, if everything turns out fine, and you have 2 distinct roots, then you just use 8.5.13 as you normally would if you go through and do this in any second order differential equation. Okay, so I just wanted to show where these came from. It's really not important after you know where they come from. You just have to be able to apply them in exams and stuff. So just brief overview of where they came from, but let's do an example now. So as an example, let's take d squared y dt squared plus 2 dy dt plus 5y is equal to 0. And then they give us an initial condition. So we'll see in a second that the mass spring systems, as scary as they look, the textbook problems at least, are pretty simple to do. And so they make us do a little bit of more work by figuring out what C1 and C2 are going to be to pin down a particular solution to this differential equation. Okay, so what do we have to do? Well, we have to determine which of these cases. First of all, C is not 0, right? So we have damping. And then I have to look and I have to determine which case of damping do I have. Do I have underdamping, critically damping, or overdamping? So to do that, I check the quantity c squared over 4km. Okay, that's the defining quality of the system. So what it's helpful to do, you'll notice that this is technically 2 over 1 and 5 over 1. You can just set your mass equal to 1, and that helps you define your other variables here. So if I set m equal to 1, then I know that c has to be equal to 2 and k has to be equal to 5. So that's just reading it straight from the differential equation they gave me. And then I know that c squared over 4km is equal to 2 squared over 4 times 5 times 1, which gives me a fifth. So I go up to this little table that they gave me. Okay, I know a fifth is less than 1. So I have underdamping. That tells me exactly what my solutions are going to be. They're going to be complex conjugate roots. And that tells me exactly what my solution will look like. And so I chose kind of a complicated problem here as an example, but I think that might be okay. So reading directly off the table then, we have e to the minus ct over 2m, c1 cosine of mu t plus c2 sine of mu t. And then they give us mu as well, thank goodness. So you don't have to do any work there. It's 1 over 2m times the square root of 4AC, not AC, 4km, still have that quadratic formula stuck in my head, 4km minus c squared. What we do for mu then is we literally just plug in these values that we found. And we should get this is equal to 2 if you plug them in. And notice that our radical here for mu is the same as our radical up here, but they just flipped it. By flipped it, I mean they took the absolute value of it. That just ensures that your root here will give you a real number, so you can have real solutions. That's just the tactic they used. So your mu gives you 2, and then you just go back up to y of t here, and you plug stuff in. So I know c is equal to 2, so I get negative t over 2, m is equal to 1, so I have c1 cosine of 2t plus c2 sine of 2t. So I've really done no math 240 in this problem. I've just read stuff off of a table. What they need you to do then is they need you to pin down a particular solution. So it's not good enough for them just to have C1 and C2 in there. And to do so, you've seen this in a homework problem actually. If you want to define a unique solution to this problem, you just have to define a original position and an original velocity of this mass here. So if you define an original position, and then you move it, or you define a initial velocity as well, there's only one path it can take following t, beginning. So what they want you to do then is they want you to find C1 and C2. To do that, you use the initial condition. So to find one of the variables, you plug t equals 0 into y, and you set it equal to 1 is our initial condition here. So let's just look for a second what happens when you plug t equals 0 in here. Well, cosine of 0 is 1, so this becomes just c1. And then sine of 0 is 0, so the c2 is nowhere to be found when you plug t equals 0 in there. So c2 vanishes. You can't solve for it in this particular case. So here you're going to find c1 by plugging t equals 0 in. But you have to find c2 as well. So to find c2, they tell you to use the initial velocity like this, and you set it equal to 3, I believe it was. Yeah. And if you follow these, you should get C1 and C2 from these boundary conditions, and you will have done the problem. So as daunting as they look, spring mass systems aren't too terrible. You have to be reading off this chart, so this is something you should definitely have on your formula sheet if we still do those on online learning. I guess we don't. But yeah, this was just a brief overview. In the next video, we'll talk about what happens when you have an actual force being applied here.